Hello guys, KNOCKCAT this side. So today we are going to solve today's GFG problem, and it is largest subsquare surrounded by X. So the problem says that given an n-cross n matrix, and we need to find the largest subsquare grid that consists of all X in its boundaries. That means this should be whole X, this should be whole X, and this should be entirely X, and this should be entirely X. So if we have a square subgrid that is entirely X, we don't actually care about between. We want to look what is the largest subsquare grid such that all of its boundaries are X. All of its boundaries are X. And since we are looking for a square subgrid, all these boundaries should be equal. That means X is equals to some number that is follows for all four sides. So I hope that you have already read the problem by yourself and you have tried by yourself. So if I look, so this we want to achieve something like this. What is the maximum subgrid possible such that all borders are X? Okay, these all are X. These all are X. And since we are looking for a square subgrid, these all four sides should be equal. This is the condition we are given with, and we need to find the maximum square subgrid we can get. So if I look for the very first example, we are given a 2 cross 2 matrix in which all elements are X. So this is an easy one since all are X, and we can actually take this 2 cross 2 matrix as possible since this entire boundary is X, and this is square matrix. So 2 is the answer from here. Now, if we look for this case, can I take a 4 cross 4 grid? Can we see if I consider this 4 cross 4, this is not a valid because this is not 0, this is 0, and this is also 0, this is also 0. But it has to be X, it has to be X, and it has to be X. If that's the case, I would have taken this. We don't care what lies in between. We are looking for a boundary that contains all X. So 4 cross 4 is not possible here. So can we do something like 3 cross 3? And if you see this 3 cross 3, you have already read the explanation for this. It says, yes, this 3 cross 3, 3 side, 3 by 3 matrix we have, and all of its boundaries are X. So we can actually get a 3 cross 3 matrix. Beneath inside we have 0, but we don't care about that. Why? Because all of its sides is 3, so we know it is a 3 cross 3 square submatrix. So now the question is how we able to achieve, how we able to solve this question. Since we are looking for boundaries and we are looking like, is it possible for a matrix? Let's say we are a matrix and actually I'm concerned about this. I'm concerned about these. Can I do something where I can actually get what is the number of X in this row? Can I get? We need something like that only. Like if I am considering this boundary, I need to I need to know what is the number of horizontal X for this row and number of horizontal X for this row, number of vertical X for this column and number of vertical X for this column. I think this is clear. For considering a square, we are actually concerned about four sides, and for these two, we are concerned about horizontal X, and for these two, we are actually concerned about vertical X. And yes, they all have to be equal and all has to be X. So if you are able to relate to this, actually we need to know the number of X here, the number of X here, the number of X here, the number of X here. Is there a technique so that we can maintain actually the number of count of X for this horizontal X and for this vertical X? Can I actually know that, okay, tell me if I'm standing at this point, if at a matrix I'm standing at this point, what is the number of X vertically? What is the number of X horizontally? Can you think of a technique? Standing at this point, it will tell me the number of X I have vertically and the number of X I can have horizontally. If you're able to think of a prefix sum, you are in the right direction. Actually, prefix sum can only help us to maintain the number of X I have till at this point vertically and the number of X I have horizontally. So let's take this case only and let's try to form a prefix array for this. So like I've already maintained a big grid so that it's become easy. So let's say I'm taking white color only. I'm at X. So if I had to maintain a horizontal prefix array for this X, let's say it is a horizontal. So for horizontal, I know, yes, I find an X. So I will make one. Again, I will find an X. How we make a prefix? We take the previous one and we add to it. So for this, answer is 1. But since we have previously 1 also, so it will be 2. Now, I have again an X. So horizontally, now, if I am at X, I know, yes, for this it has 1 and 2 I have in previous. Yes, previously I have 2x. So this would be 3. This 0. For this, the answer is itself 0. So this is not actually forming an prefix sub array because if I can actually consider a 3 sub row, but I cannot consider a 4 row because this is not x. This is 0. Now again x, 1. 0, we cannot consider this. Again x, so this for this the answer is 1. This is 1. It will look, do I have previous x? Yes, it has. What is the value of that x? It has 1 and its own value is 1. 1 plus 1 is 2. Again x and x, for this it is 1 and for this it will be 2. For this will be 3. And I think you can relate actually. This is actually not, let's say I'm maintaining prefix sum for this row. Prefix sum for this row. So it is 1 because again this is 1 and we have previously, so it is 2. Again for this I would be 1 and because we have 2 previously it would be 3. So this is nothing but prefix array and here it is matrix. Now we have 0. It itself is 0. So how it can make a bigger subtract x? It can only 0. Again for this x we know 1. 0 came to 0. 1 came, okay. For this we have 1. So we'll look, do we have a previously? Because we want to make it large. So we will look, yes we have, so 2. So this is, we have maintained horizontal player. So now if I want to know at this point, what is the maximum horizontal I can get? So I can actually get 3. I think this much is clear. Okay. Now, since what I said here, we also, like if I'm at this point x and I know the horizontal for here, for finding the value x, do I should also needing the vertical value because square needs 4 sides. So if I know the horizontal value, the maximum x I can have, do I don't need the vertical path? We also need that. It cannot be the possibility that you know x and you will able to form a square using this only. We should be knowing this also. Then we look what we can do next. So now we know horizontal. So let make the vertical array here only. Vertical array here only. For vertical, this is our one row. This is actually our row. This is actually our row. I think you able to relate. Horizontally, we are looking for this, but for vertical, we need to maintain the, from top to down. So if I maintain a prefix array for this vertically, let's take it is a pair of vertical now. So let me take a different color. Vertically, if I am at this row, I know the answer is 1. Again, if I am at this, I know the answer is 1. Again, we know it would be 1 because we have x and previously we don't have any row. So it cannot be like accumulating over it. Now we have 0. This will be 0 only. Now, when I'm at x, this value is 1. So to maintain the larger subgrid, I will actually look to ask for its previous value. That are you 1 or what the maximum value you have formed? What the maximum value you have formed? So for this one, if I came here, for its the value is 1 and it will look for a value 1. So it would be 2. For this we have 0, 0. For this x, we can have 1 and since we have 1 above also, we can have 2. For this we have 1 and above we have 0. So like 1 we can form. From here, we have 1 for this, but above we are forming 2. So this will be 3. For this we have 1, above we have 0. So 1, 0, 1, we get 1 only. For this we have 1, but above we can form 2. So this will form 3. Now here we are forming 0. It is actually 0. Here 1, 2, we can form 1. And if I look, we are forming of 3 and I can form 1 from this also. This will actually form 4. For this 0, This will be 0. For this x, we can form 1. I will look, can I get previously? Yes, can make 2 byte rate 4. This time it is 1. We will look, okay, we are getting 0. So the maximum we can get 1. Now I have horizontal and vertical here. So what we are looking for. Now, if I say I am at this point, I am at this point. So can I get to know the maximum horizontal I am forming this thus far? So 2. Yes, 2 is the maximum horizontal I am forming this far. And the vertical, uh, okay, sorry, 1 is the horizontal one. So I know the maximum I am forming here would be a 1. Horizontally, I am forming 1. And vertically, I am forming 2. Vertically, I am forming 2. That means 2. And the minimum of them would be 1. Minimum of them would be 1. Because how can, like, the same thing that like, if I am at this point, and from here I got 4, and from here I got 3. So, if even though if I get 3 from here also, is this a possible square matrix? The answer is no. 4 cross 3 is not a square matrix. So we can only consider a minimum of this. We can only consider minimum of them. Let's take I'm at this point. From here I am getting 5, and from here I am getting only 2. Although if we say geometrically it looks like they both are equal, but let's say this is 5 and this is 2. So can you actually make, okay, you can get 5 from here, but you can only get 2 from here. Do this form a square matrix? It will never form a square matrix. But yes, if you consider the minimum of them, if you consider the minimum of them, there might be a possibility that this will form a valid square matrix. Okay, this form a square matrix. This is a guarantee that this will form a square matrix. Why I say valid? Because the validity in this case is for looking for boundaries x. So if I am here, I know 1 is the horizontal and 2 is the vertical. So that means 1. That means 1 square matrix I can get, and 1 is the answer. So for that, let's consider from the very behind. We will look from the very end. We will actually look from the very end, and let's say I'm at this index. I know the maximum vertical I can get is 2 from now, and horizontally I can get 1. So that means 1. You can only get 1. No need to worry. This is interesting. This looks interesting. So here we have actually 4 vertically. Here we have 4. So that means I can actually get 4 from vertical, and from here I can only get 1. So minimum is 1 only. We cannot actually get 0. Here also we can get only 1. So our answer is 1 till now. 0. Here we are getting 3. It is saying from here I can actually get 3 from vertical and 3 from horizontal. That means 3 from vertical, 3 from horizontal. Because what this state? This actually states 3 is horizontal. Over this I can get 3. And if you can see, yes, we are 3 here. And if you see this horizontal one, this is actually 3. That means 3, 3 is a valid pair. And I can actually look for this submatrix. I can actually look for this submatrix. Okay. So 3 cross 3, that means this is a very possibility. So, okay, if I look for 3, okay, if I look for a 3, so if I somehow come to here, 3, let's say now I came to this block, okay, and from this 3, I can come to here, this 3, okay, we know, yes, this part will form a valid subsquare. This part will form a valid subsquare. Okay, this part we know, this entire part, this part, if you can see, yes, this part we know, this part will form a valid subsquare. Why? Because horizontally we have also 3, and vertically also we have 3. So if somehow I am at this point and I am at this point, can I actually know what the maximum horizontal you are getting? From here, what the maximum horizontal I am getting? You will find, we know, we are very sure about this. Yes, this will form because we have actually find two sides which are equals to x, like not equals to x. Since we are taking minimum of them, so we are taking minimum of them. In this case we are getting 3, but given 4 and 3, we have already looked for minimum 3 only. So let's say we have minimum of that. That means minimum of them, both of them, this part is actually forming a square. But now we cannot say actually that if we have got this, this will also form a valid square. But if I somehow jump to this point, and if I somehow jump to this point, I know we are maintaining a pair of horizontal and vertical. I know we are maintaining a vertical pair. So from here, we know vertically it is forming. This point no, horizontally it is forming, and this point no, vertically, horizontally. This point no, let me make it to center. This point actually no, this point no, vertically it is forming, and this no, horizontally it is also forming. So vertically if I move to this point, and horizontally if I move to this point, now if I somehow get to know what is this forming, so this point horizontal will actually give me this point horizontal will give me this, and if I'm at this point, I want to know this, so this point vertical will give me this point vertical will give me this. And if both these points, if both this horizontal and vertical are greater than is equals to the horizontal and vertical I get from this point, because if it is 3, if it is 3, okay, if it is 3 and this is 3, then this also need to be at, at least 3, at least 3. It can be greater than, because let's say it is the entire subgrid. Like if we consider this case also, this can be a case that this is an entire subgrid. So if I am like looking at this point, let's say if this is also x, and we are actually looking for this, and let's say we are at x here, so this complete x till now has to be greater than equals to 3. Why? Because if it is was 2, if it is was 2, that means it is forming till here only. If it was 2, it is forming till here only. So do it will form a valid square. Do it form a valid square? No, it will not form. So at least I get to know vertical from here, horizontal from here. So if for this point, if for this point I get to know the horizontal distance, and if for this point I get to know the vertical distance, and these 2 points are actually this horizontal and this vertical are actually greater than or equals to this HV value that we have from here. In this case, we have 3. So if we find these two, that yes, these two also follows the condition, that means this entire subgrid we have formed. This entire subgrid we have formed. So in this case, you can actually see, yes, if you look for this horizontal distance, you will get 3 from here. You are getting 3 from here, 3. That means 3 is fine. And if you look for its vertical, if you look for its vertical, you can also see, yes, it is also forming 3. So yes, our current answer, we are getting one earlier. We are actually getting one earlier, but now our answer is 3. Now we have gotten a good pair. So that is actually, we have got a 3P. Now, what if we don't have got this? Let's say, what if we have don't got it? And I'm like just making some manipulation. Let's say it was 2. Okay. Let's say it was 2. Let's say it was 2. So now I know this 2, from here I'm getting 2, and from here I'm getting 2. This 2 and 3 are not forming actually 3 from here. So this cannot be a case. So can I look for, can I look for this submatrix? Can I look for this submatrix? Yes. Now we can look for, if this is not the case, because this tells us that there might be a possibility, because horizontally and vertically this we have formed, and there might be a possibility that we can find this also. So if we don't find, so let's say here is 2, so 2 and 3 will never form a square matrix. So what we will do, we will look for this one. We will now we will look for this square matrix. We will look for this square matrix, and if you look for this square matrix, we know this is already 3. So this time it will be 2. It will be 2. This time this part will be 2, and this part will also 2. So now if I jump to this point, if I jump to this point and I ask, tell me your horizontal, tell me your horizontal, and it gives, it gives 1, and this 1 is less than 2. That means this will not form a square matrix. And if you ask this one, tell me your vertical, it is 1 here, and this 1 is also less than 2. That means this square matrix will also not form a particular square. And if this do not form, now we will look for this small square matrix. We will look for the square matrix because, and this time we will look for 1. Why? Because now we know when we look for 3 cross 3, we don't find. Okay, because these two find the condition. Now I look for 2 cross 2, this also don't. So now look for 1 cross 1. And for 1 cross 1, if this is x, it is already an answer. So I hope you are getting. I hope you are getting. So let me. So similarly, if it would have checked this, it would have checked this, it would have checked this, like entirely this will check the same thing. And at some point, this will check the same thing. And if at some point it finds an xy, so it will look for minimum of x comma y. So it will look for these 2 points. If these two settle, so we have got a larger, we don't need to check for these small. If at the beginning only these 2 points get settled, that it's horizontal and it's vertical, it this is vertical. If at the beginning only it's horizontal and it's vertical, find setup, then we don't need to look for this. But if don't find, then at next time we will look and check if this horizontal and this vertical forms. If not, then we look for this submatrix. If this horizontal and this vertical forms, that's how this will work. And what we need to do, like if I had to guess this problem, we know the horizontal and vertical count for this. So we take the minimum of both. So if I know 3 is forming from here and 3 is also forming from both of them. So can I move to 3 here? I will move to here. Can I move to 3 here? I will move to here. So now if I want to know this, can I actually ask, tell me your vertical count. Tell me vertical count. Okay. And if I want to look this, can I ask, okay, tell me your horizontal count. Tell me your horizontal count. So if it tells me, and both of them, both these x and y are at least greater than or equals to this, the value we are looking for. If it is follows, then this is our answer, and we don't need to check here because this will give us minimum only. We will look for maximum. So if this follows, why to come check for why to check for 2 cross 2? Why to check for 2 cross 2? But if it do not follow, we will check for 2 cross 2. If they do not follow, we check for 1 cross 1. So this is how we will follow this question. So I think I have explained this in a very good way that if you know xy and you can actually ask its x, which is already in prefix array, and you can ask this y, which is already in this prefix array. So if I come to the code part and let me retrieve my own code. So I have done nothing. I have just make the here. I have make the horizontal function get vertical prefix, get horizontal prefix. So vertical prefix, if you say, I'm just making a prefix sum, that this is just prefix sum. You should be knowing this. I is 0. If I is 0, then it would be like if it is x, give it as 1, otherwise 0. And else part, if it is not 0, we will first check if it is x. So if it is x, I know the answer is 1 for this. And if it is 1 and this is not 0, because if it is not 0, that means for this vertical, there is an other row also. So I will look for previous value, this previous value and add 1 to it because for this 1 is already an answer. For this how I have make vertical array. This I have making horizontal array. Now I'm editing from the very behind. Why? I told you if I'm at xy and I know the minimum of both. So I'm iterating. So from here, I know the minimum possible value. That would be the minimum of that I got from vertical. So let's say x I got from here. Now what we are doing? We are checking is this possible. So I did the same thing. Largest square grid because currently this is my 0. Maximum I can get is 0. I checked. Okay. Current possible value. If it is 1 also, it is greater than 0. So I will check. Okay. If it is 1, let's see. If it is 1, that means 1 hop, 1 hop. So this is this only, and this is x. We have already got 1. So I'm actually checking the jump. The jump we are, let's say it is 4. This value is coming 4. So I'm checking if it is greater than my, that means this can be a possible answer. So I jump to 4. I jump to 4. The same thing I'm doing here. Let's say I'm at ij. I'm at ij. Okay. And if I have to jump 4 vertically, I will actually do my I minus 4 plus 1. because I minus 4 will bring me here and plus 1 I will have to come here. Same thing, I minus current value plus 1. You try run this in your mind, okay? And j will remain same because we are looking for this point. And this is vertical, horizontal. I'm at this point, x, y, vertical, horizontal. I want to know this, vertical, horizontal. And this is horizontal, vertical. I want to know this. So I'm checking, okay. So this value I will actually get from column will remain same, but row will be this. And for this, row will remain same. Row is I only, but j is the possible value. Let's say we are getting 3 from here. So minus 3 will bring here plus 1. This is the possible value. So we will, so I am checking, okay, for this I, for not this I, like this is the jump actually. This is actually the jump. So because I am at I, this will tell me I want to know this value. I'm not looking for this value. I want to know this value, and this jump will give me, and I'm coming here. This will give me this value. That what is the vertical is coming from here. This point will give me the vertical. So but that's it. So if vertical value is greater than my current value and horizontal value is also greater than my current possible, then I can update to maximum and break. Why break? Let's say if I've already found this, why to look for minimum? But if that's not the case, I am doing current possible minus 1. That is, if I'm earlier looking for 3, now I will look for 2. Now I will look for 2. And that means the jump will be here only. The jump would be here. And now it will compare these two values. That if it is horizontal and it's vertical are greater than 2 or not. And similarly, at the time it is greater than, it will this while loop run. And at the end, I can return the largest subgrid. Now coming to the time complexity. So the time complexity, if you look, making this vertical and horizontal prefix array is n square because we are making prefix arrays for both. So n square this is. Now for this loop, it looks like n cube, that I am iterating n here, and another n here. Now think of this. Let's come to here only. Let's say if I have this grid, okay, if I have this grid and I am looking for, and I'm at this point. So let's say I get 4 from here and 4 from here. That means this is satisfying. So I will jump here and I will jump here. And now let's say these 2 points do not follow condition. So now I will check for these points and these points. Okay, actually I did wrong something. We have make a 4 cross 4 grid. Okay, let me erase this. We have make a 4 cross 5 grid. Let's say this is the matrix. Okay, so if this is following the condition, I will actually look for this point and this point. So if they do follow the condition, so that is right. But let's say it do not follow. We have already one iteration. So I will check for this one and this one. Let's say it do not follow again, second iteration. Then it check for this and this, third iteration. And then it's check for this element. So 4 iterations. So this actually check for n iterations. This actually check for n iterations. And if you look for here, already we are looking going down n square. And if this one is also taking n, then it's make n cube. But what if I tell you that this n is not every time? For this case, yes. For this case, it is running n times. But what if I was looking for this? So from here the maximum I can get would be 3, and from here the maximum I can get is 4. But since it can only check for 3, it will only check for 3. That means this time it will check for these 2 points, one iteration again. Then if not follow these 2 points and these 2 points, so it will go for 3 iterations. Earlier it got for 4, now it goes for 3. Now let's say, now I came to, let me erase this. Let me erase all these. Just 5 minutes on, and I just boil down the time complexity for you. So now, if I'm at here, so I know even if I go 4 from here, but here I can only get 2. So 4 and 2. So it can only run for 2. It will check for these 2 points and that's this point. So 2. So if you find it is actually running for 4 plus 3 plus 2 plus 1. This is not running 4 plus 4 plus 4 plus 4. Okay, for this row, when this row will come, it is already 3, and from here it got 4. So that it will only run for 3. Even if it is here, we will check for a minimum. From here it is getting 3, here it is getting 3. So the first time it runs for 4, 3, 2, 1. For this row, it will actually run for 3 plus 2 plus 1. For this row, if I'm at here, from here it can only get 2. From here it can only get 2. I know it's have become like confused. It can only go from 2 here. From here it has 4, but from it has only 2. So we will only check for these 2 points. So next time it will be 2 plus 1. So we are not we will not think of the entire iteration, but in a nutshell, you now know that the loop is eventually, for the very first time it is running, for the very first time it is running n, n minus 1, n minus 2, n minus 3. So for this row, it actually don't run for n into n plus n. But what is run? It run for this, and this is nothing but AP. It is an. And if let's say I have 6, so if these, let's say 6 cross 6 matrix, so the iteration would be gone. What the iteration it has done would be 6 cross 6, 36. Okay, 6 cross 6. Like what it feels like if it is the n square, and when we iterating for this inside this, if it has taken all have taken 6 times, then it has taken 36 times. But it will not take. It will take AP, and you know the terms for first 6 terms will be 6 into 7 by 2, so 21. And 21 is way lesser than 36. And the next time this 21 will even reduce to more. So eventually this loop is not running order of n, but this loop is running order of a of n times for the, let's say, n4. Next time it is running a of n minus 1 times. Next time it is running a of n minus 2. So this is not actually n. This is not actually n plus n plus n. This is 4 times 4 is not equals to a of 4. You can see 4 times 4 would be 16, but sum of 4 terms would be 4 into 5 by 2. It is 10. So for 16 and 10, later you'll find this difference is very less. So comparatively, if you see, this outside loop has more time complexity in terms of this, because this inside loop has only complexity of a of n for this iteration. Next iteration, it would be having a of n minus 1, and that's why it has more dominating factor. The outer loop is running more times rather than this, because this is only running for a of n times, and that is only when we are talking about this last element. Worst it can go for n times, because next time you are at here, it has already reduced a of to a of n minus 1. So this is not actually. So you can see maximum it runs for n times here. Maximum it can do run for a of n minus 1 times. Next time it can run for n minus 3 times. So that's why this is order of n square only. And if I have to write the time complexity, so time complexity is for this approach is order of n square, not n cube. Why I have already tell you, it is actually order of n cross n plus a of n. And if you tell it is n only, so you can say it is n square. Okay, and the space complexity is order of n square. Well, we know that we have taken 2 prefix arrays. So this is the thing. This is the thing, and I hope I will able to explain you the problem. Last, if I have to say something, x, y, vertically, horizontally we know, but now we want to know for this point the horizontal distance. For this point, we want to know the vertical distance. So if they do meet, break, because checking for minimum will not increase our answer. But if do not follow, check for lower subgrade. So that's all. And I hope I able to explain you this problem. So thank you, and knock at this side.